Hello. In this video, you are going to learn how to do a one-way ANOVA. As you can see, our list of items that we have covered in this video is getting longer. You now know how to use R, and you know how to run a couple simple statistical tests. Today, you are going to add another statistical procedure to your skill set. An ANOVA, very simply, is a way to see if there are any statistically significant differences between the means, or the averages, of three or more independent groups. This way you can use a one-way, which means only one independent variable, analysis of variance, or ANOVA. ANOVA is short for analysis of variance. The one-way ANOVA is called omnibus. It's an omnibus test statistic and cannot tell you which specific groups were significantly different from each other. It only tells you that at least two groups were different. To figure out which groups, or all groups, were different, you should run either the post hoc or planned contrast tests. And we will talk more about what these things mean throughout the video. This is just meant to put these words in your mind a little bit, but we'll also talk about them more later. To run the post hoc test, if you have no specific hypotheses about the differences between the groups, or you are interested in investigating all possible pairwise comparisons. So, to say that again, we use the post hoc contrast test if you're not sure which particular group might, or which set of relationships leads to your statistically significant differences among groups. On the other hand, if you are sure, or you have a very specific sense of it, you can run the planned contrast test. For example, if you have a hypothesis that there is a difference between group D and group B, or between other groups. That's a basic overview of the ANOVA. Now let's get into R and see how we would actually do it. First, under Import Your Data, here is a description of what the data we will be working with today are. Remember that these are not real. They're only for educational purposes. Imagine that you have three groups, 1, 2, 3. Group 1 is attending or going to an on-site ESL class. Group 2 goes to an online ESL class. And Group 3 goes to a class that has both on-site and online parts. The outcome is their performance on a Motivation for Learning ESL questionnaire, a survey. The questionnaire is a Likert scale with responses ranging from 1 to 10. The question is if these learners in the three different groups are different in terms of their level of motivation for learning ESL. The hypothesis is that the ones in Group 3, the hybrid class, have a higher level of motivation. Here we are not making any causal inference, meaning we're not claiming attending a hybrid class increases motivation. In fact, the opposite may be true. The ones with higher motivation may choose to attend the hybrid classes to begin with. So, it is important to emphasize here that we want to figure out if they are different. And with the current data, we can't answer the question of why they are different. The first step before you do your ANOVA is to get your data into R. So here, let's start by running this first line of code, which reads in a CSV file. I've already got my data in, so I won't run it, but you can go ahead and run it. And then I'm going to run this to take a look at the data. As you can see, we have two columns. So instead of having, for example, three columns splitting up the 1, 2, 3 groups, we simply have one column where the group number is written, either 1, 2, or 3. And next to that, we have the motivation score on the Likert scale. Another way to do this would have been to have three columns, and these data would have been in column 1, these data would have been in column 2, and these data would have been in column 3. I'll talk more about that in a little while. Next up, after we bring in our data, we have our assumptions to talk about. I won't go into depth about each assumption here, but you should pause the video and read about them. The first assumption we'll go over, though, is that we shouldn't have any significant outliers. Before, we've looked for outliers using a box plot, and we'll do the same thing here with our data. Whenever you look at this box plot, though, you can see that there's a problem. Because we brought the data in with two columns, the box plot is showing two columns. One of the columns is just a box plot of 1, 2, and 3, these numbers. And the other plot here shows a box plot for all of our data without separating it into different groups. What we want is to look at three different plots like this, one for each group of our independent variable. So we have a couple of options in order to get to a better box plot that gives us what we want. Number one would be to go back to this stage and re-enter our data into our Excel or CSV file so that it is in three columns. This is the easier option. You could just go in, usually in applied linguistics, you're dealing with smaller data sets. So you can go in and manually do this in Excel. But for learning purposes, I did it manually in R to show you how you could do it. Just remember that this is just one way to take the data as it is and make it into a workable form for the box plot and for your summary statistics. But there are other ways to do what I'm about to do. In a programming language like R, there's always more than one way. Here I wrote a custom function, and the purpose of this function is to take our data and split it or break it apart into three different vectors according to the group. So I'm not going to go through this code in detail, but I do recommend pausing the video and trying to understand it for yourself. You have the skills to understand this code based upon watching, if you've watched the videos from the beginning, the series from the beginning. So none of this code is especially difficult, but it does require you to look at it and think about it and try to understand it a little bit. So I do recommend doing that. But for now, just realize that what this does is temporarily take your input data, and this is your input data here, and it divides it according to group. Now, the way I've set up this function is that it also automatically prints out our summary statistics, because you also need to look at each group individually for your summary statistics. And it also prints out the box plot automatically. So, to summarize what I just talked about, remember that The easiest option to do this is just to go into your Excel file, and you could just take these numbers and put it in column 1, take these and put them in a second column, and take these and put them in a third column. And then re-import it, and there you have your data separated into different groups without having to do it manually. But if you were working with a huge data set, that would be more difficult. And maybe your data aren't in an orderly fashion. Maybe it's more complex for some reason. In these cases, you could write some sort of function in R that allows you to work with the data from within R. Also, do visit some forums and look at good R code out there in order for good examples of how to do these sorts of things. There you'll learn what are the conventions and what are the best practices involved with writing functions like this. In any case, we'll run my function. And now you can see that we have a box plot that looks right. We have 3 groups, 1, 2, and 3. And we also have an output of our descriptive statistics for each group. As we can see, there are no outliers. An outlier would be a little circle outside of the whiskers. These are the whiskers. So we're good with that assumption. So let's move on. And I'm going to delete this little piece of code that doesn't need to be there. The next assumption that we'll work with is the homogeneity of variances. We need to import our CAR, our companion to applied regression, using the library function. So go ahead and execute that. And then in order to work with our data in the Levine test, this is how I chose to do it. So I converted our input data as data frame, and then I added column names into the data frame with this function, and then I put each of the columns, our dependent variable and our grouping variables, our independent variable, I pass those into the Levine test as numeric and as character, because this is what the Levine test asks for. And then when I run all this code, I've already run it, so I don't need to run it as a whole, but I will for learning purposes. I can just run it all, and we can see that our Levine test statistic is 0.1337. And because this is not significant, it means that we have met this assumption, and we do have homogeneity of variances. And so we can move on. I'll go ahead and collapse this piece of code so that we can see everything more easily. And this one too. Now we're going on to running the one-way ANOVA. This is the code, very simply, to run an ANOVA. It looks pretty straightforward. Here I save it to a variable and then pass that variable into the summary function in order to give us something that's more readable. So I'll run that. As you can see, we do have a significant outcome for our ANOVA. Remember, we talked about at the beginning that the ANOVA is an omnibus test statistic. So this is statistically significant. However, we don't know which of the 3 groups is actually statistically significant from the others. So it could be that all 3 are statistically significant in terms of their means, or it could just be that group 1 and group 3 are, but we don't know yet. In order to find out, we run some sort of post hoc test, and here we run the Tukey test. And then we look at the outcome. And here, this table does indeed show us the outcome of this. And here are our p-values. So we can see that only one of our three p-values is significant. And on the far left, we can see which groups are being compared. So here in the first row, group 1 is being compared to group 2. So here we have these two groups. The second one is group 3 and group 1. So here we have group 3 and group 1. And the third one are these two groups, 3 and 2. And then we get a couple of numbers, and this one is an important one. So here we see that only the difference between group 1 and group 3 is statistically significant. The others are larger than 0.05. So here we know that the mean of group 1 and the mean of group 3 is statistically significantly different. Whenever we're working with groups that have different n's, and n, capital N, is a representation for the number of members in that group. So whenever we're working with groups that are of different sizes, you want to use the Tukey-Kramer post hoc test, not just the Tukey. In this example, the numbers come out correctly. So R is either working behind the scenes to convert the numbers into the correct test, or they just happen to come out correctly. And I double checked these numbers against SPSS numbers. So we know that they're correct, but do know that if the different size of your groups are different, you want to go with the Tukey-Kramer test and not just the Tukey, which is designed for groups that are of the same size. Next up, we want to think about another assumption, and this is the assumption of normality. So we run a few pieces of code to get to the Shapiro test, which helps us with considerations of normality. And we can see that the Shapiro-Wilk normality test is not significant. So therefore, we've met the assumption of normality. And next, we'll calculate an effect size here, and this specifically is the omega squared statistic. In order to run the omega squared, we need to install a new package, load that package, and then run the code. I won't install again, but you can take a second and install that. I'll just run these two pieces. And we can take a look at the effect size. 0.367. And that is about it for the ANOVA. I pulled a lot of this code and borrowed quite a bit of it from this website. So I want to give credit and reference to this website. Please visit it if you want to learn a little bit more about R and how to do different statistical tests. It's helpful always to include your variables at the end that you'll be returning to later. We should probably add one here for the normality assumption. So I'll just run that code and then copy this variable, and we can put it somewhere that makes sense, like up at the top, so that whenever we run this whole bit here later when we return, you can see that this is all of the good information that you would need if you were writing a paper, for example, and you needed to include these in your paper.